going to discuss more on tray towers. So I will discuss tray towers, but I think I'm sick. Therefore, I have a friend here that can discuss about tray towers. This is Teacher. Say hi. Hi.
Entrainment in tray or plate towers. Entrainment is the liquid transported by the gas of the tray above. It reduces tray efficiency by the counteraction of the mass transfer process experienced by the liquid in the lower tray that contains more of the less volatile components. Sometimes, it tends to contaminate the overhead product by bringing non-volatile impurities upward. Moreover, it has a tendency to damage the rotating machinery in the path of the overhead product. Entrainment can be affected by several factors such as gas velocity, liquid rate, and other variables such as tray spacing and hole diameter. Entrainment increases with gas velocity to a high power. Generally, smaller power is indicative of a relatively gradual change, are typical of low-pressure systems. On the other hand, steep changes in entrainment that are typical for high-pressure systems indicate higher powers. As the liquid rate is raised at a constant gas rate, entrainment first diminishes, passes to a minimum, and then finally increases. At lower liquid rates, an increase would suppress atomization, drop formation, and then entrainment, while at higher rates, an increase would reduce effective tray spacing, which increases entrainment. Entrainment decreases as the spacing of the trays increases. Entrainment increases with hole diameter. The effect of hole diameter depends on the flow regime. If it is pre-regime, the effect is large. If it is front regime, the effect is small. Pressure drop in tray or plate towers. The total pressure drop across the tray can be calculated using the formula HT equals HD plus H prime L. Again, the formula is HT equals HD plus H prime L, where HT is the total pressure drop in millimeter liquid, HD is the pressure drop across the dispersion unit, dry hole for sieve trays, and dry valve for valve trays, also in millimeter liquid. HL is the pressure drop through aerated mass over and around the dispenser in millimeter liquid. Pressure drop across the disperser can be calculated using HD equals K times rho G over rho L times UH squared, where UH is the linear gas velocity through slots, valve trays, or perforations, sieve trays, in meters per second. K is equal to 50.8 over CV squared, where CV can be taken from figure 14-35 of Perry's Chemical Engineer's Handbook, 8th edition. The figure shown in this slide is figure 14-35 of Perry's Chemical Engineer's Handbook, 8th edition. It shows the discharge coefficients for gas flow in sieve trays. It is used to find the value of CV needed to calculate for the pressure drop across the disperser. Other hydraulic limits. Weeping is the liquid descending through tray perforations, short-circuiting the contact zone and lowering the tray efficiency. It occurs when the static head, used to push liquid down perforations and is counteracted by the pressure drop that holds the liquid on the tray, overcomes the pressure drop. Weeping is mainly affected by the fractional hole area. When the area is larger, gas pressure drop is smaller, and weeping tendency increases. Dump point or seal point. As gas velocity is lowered below the weep point, the fraction of liquid weeping increases until all the liquid fed to the tray weeps through the holes and none reaches the downcomer. Weep point is the gas velocity at which weeping first becomes noticeable. Turn down. The turn down ratio is the ratio of the normal operating gas throughput to the minimum allowable gas throughout. Vapor channeling. When the vapor channels through a tray region, because of high vapor velocity, premature entrainment flood and excessive entrainment happens. At this point, other regions are being deficient with vapor and tend to weep. This event lowers tray efficiency. Tray efficiency. Overall column efficiency. The overall column efficiency, or E sub O, involves the whole tower. It is simple to use but least fundamental. E sub O is equal to the number of ideal trays over the number of actual trays. The Murphy tray efficiency, or E sub M, is equal to y sub n minus y sub n plus 1 all over y sub n star minus y sub n plus 1, where y sub n is the average concentration of the mixed vapor leaving the tray n, y sub n plus 1 is the average actual concentration of the mixed vapor entering tray n, and y sub n star is the concentration of the vapor that would be in equilibrium with the liquid of concentration x sub n leaving the tray to the downcomer. The point or local efficiency, or E sub MP. E sub MP is equal to y sub n prime minus y sub n plus 1 prime over y sub n star prime minus y sub n plus 1 prime, where y sub n is equal to the concentration of the vapor at specific point in plate n. Y sub n plus 1 prime is the concentration of the vapor entering the plate at the same point. Y sub n star prime is the concentration of the vapor that would be in equilibrium with the liquid of concentration x sub n prime at the same point. Figure 11.5-1 of Gian Coplis shows the vapor and liquid composition on a sieve tray and tray efficiency. In getting the point efficiency, y sub n prime cannot be greater than y sub n prime star. Therefore, point efficiency can only be less than or equal to 1 or 100%. In small diameter towers, the vapor flow sufficiently agitates the liquid so that it is uniform on the tray. Then the concentration of the liquid leaving is the same as that on the tray. The point efficiency then equals the Murphy tray efficiency, where E sub m is equal to E sub MP. In large diameter columns, incomplete mixing of the liquid occurs on the trays. Some vapor will contact the entering liquid x sub n minus 1, which is richer in component A than x sub n. This will give a richer vapor at this point than at the exit point, where x sub n leaves. Hence, the tray efficiency E sub m will be greater than the point efficiency E sub MP. The value of E sub m can be related to E sub MP by the integration of E sub MP over the entire tray. There are several factors that affect tray efficiency. First, errors in vapor-liquid equilibrium. At very low relative volatilities, small errors in vapor-liquid equilibrium have a huge impact on the tray efficiency. Next, liquid flow patterns on large trays. Liquid crosses the tray in plug flow with superimposed back mixing, and that the vapor is perfectly mixed. Increasing the tray diameter results to liquid plug flow and suppresses back mixing. Another factor that affects tray efficiency is the wear height. Taller wear height increases the liquid level in the tray, both in the froth and emulsion regimes, increases the interfacial area and vapor contact time, and increases efficiency. Another is length of liquid flow path. Efficiency increases if longer liquid flow paths enhance the liquid vapor contact time and the significance of the liquid plug flow. The fractional hole area also affects the tray efficiency. A decrease in the fractional hole area results in an increase in efficiency. Next is the hole diameter. The effect of the hole diameter in efficiency is small or sometimes negligible. Vapor-liquid loads and reflux ratio. These things have small effects on efficiency. Viscosity and relative volatility. When there is a decrease in viscosity and relative volatility, there is an increase in efficiency. Maldistribution. It can cause reduction of efficiency in multi-pass trays. Efficiency slightly increases with pressure. At pressures greater than 10 to 20 bars, at high liquid rates, vapor entailment occurring into the downcomer becomes significant, and there is a decrease in tray efficiency.